Hey guys, so in the last lecture of magnetohydrodynamic power plants MHD, we have seen the concept that how MHD works, that how the directly the energy is converted into electrical energy, that kinetic energy of the particles are converted into electrical energy. So that we have seen. So today we will see the thermal efficiency of MHD cycle. So in overall power cycle, a compressor is used to elevate the pressure. Heat is added at a high pressure and flow is accelerated before entering the converter. So let's draw schematic diagram. So suppose this is an heater. So here heat is being added. So suppose QH amount of heat is added, then it moves towards the expander, that is generator. So here the electricity is being produced. So this is we will call as generator. So here it is coupled with a resistance of load RL, and here from here the power is being produced from the generator. Then this will move towards cooler, so COOLER, cooler. Then the gas will move towards the compressor. So this is the compressor. So here work has to be done. So WC, and then it will move towards the heater. So let's divide the cycle in 1, 2, 3, and 4 stages. So now let's draw the TS diagram for this MHD cycle. So suppose on the x-axis is entropy, it is S, and on the y-axis is temperature T. So if we draw the TS diagram, so we'll get that. So from 1 to 2, so 1 to 2 processes, heat is being added, so temperature will increase. Then 2 to 3 is power generation, so temperature will reduce at constant entropy. And then 3 to 4 is again cooling process, so the heat is being rejected. And then 4 to 1 is compressor process, so the temperature will increase. So let's say 1, 2, 3, and 4. So this is 1, 2, 3, 4. These are the uh, so this is an ideal cycle. So let's give the real cycle. So just for the ideal cycle, we'll just rename 1 as 1 dash and 3 as 3 dash. The real cycle will be somewhat, 1 will be here and 3 will be here. So this will be the real cycle. So the overall efficiency of MHD power cycle is limited by a Carnot efficiency. So in terms of TS diagram, so we'll write as efficiency is equal to work output upon heat input. It is output upon input. So let's do the work output. So where we are getting the output? So output we are getting in the expander, that is generator, that is 2 to 3 process. So we will write here as h uh, h uh, h02 minus h03. So this is the work output minus work input. So we are giving input in the this compressor, so that is 4 to 1 process. So we'll subtract it as h01 minus h04. And what input, heat input we are giving? So heat input we are giving here in the heater, so that is 1 to 2 process. So that is h02 minus h01. So this is the efficiency. So where the indicated enthalpies are stagnation values which take into account of the kinetic energy of the flow. The stagnation enthalpy can be defined as h0 is equal to h plus u square by 2. So this is u is velocity of the flow. So this is the h0. So so now we'll solve an example which was asked in exam. So suppose this is the example. So calculate the open circuit voltage. So what we need to calculate is voltage, that is open circuit. So we need to find out E0. So that is open circuit voltage. And what is E0? That is BUD, as we know that BUD. So open circuit voltage and maximum power output. And what next we have to find out, that is P max. So P max also we need to find out. So P max, as we know that it is E0 square by 4 rg. So we need to find E0 first to find out P max of the MHD engine with following specifications. The specifications are given. So what are the specifications? So first is first specification is plant area. So as area is A, so area is given as 0.2 meter square. Then distance between two plates, so that is small d, that is 0.4 meter. Then flux density, that is magnetic flux, that is B. Then average gas velocity, that is small u. And conductivity of the gas, so that is sigma. So all the terms are given. So we will start with E0. So E0 is BUD. So what is B? So E0 will be equal to B is 2 into U is 1000, 1 2 3, and D is 0.4, so into 0.4. So the open circuit voltage E0 will be equal to 800 volts. So it is 800 volts. So now we need to find P max. So P max E0 we have for P max, but we don't have Rg, that is resistance. So generator resistance we need to find out. So what we will do? So we will so the formula for finding Rg is, it is Rg is equal to, what is Rg is equal to d, small d, upon sigma A. So the distance between the plates, that is 0.4, divided by sigma A. Sigma is 10 mole per meter into A area. Area is 0.2. So it is uh, so it is 2 by 10. So it is 0.2. So it will come 0.2 ohm. 0.2 ohm. So we got resistance as 0.2 ohm. So now we will find out P max. So P max will be equal to 800 square divided by 4 into 0.2. So this will be equal to 800 kilowatt. So this is equal to 800 kilowatt. So this is the Pmax value. So the both terms which we needed to find out, we have found out, is Pmax and E0. So this solves our problem. So I hope you understood. So now we'll see few of the advantages and disadvantages of MHD power plants. So what are the advantages and disadvantages? So advantages of the MHD power plant. So first is MHD steam hybrid plant is highly efficient. So the efficiency is very high, nearly equal to 50 to 60 percentage. So the fuel is better utilized. The second benefit is that the system has no moving part. So hence it is more reliable as it has no moving part. Then the third is that the closed cycle system produces power free of pollution. So no pollution in closed cycle system. Then fourth advantage is that the MHD generators have low specific weight. So the specific weight is low. So it will result in rapid start. So rapid start, high power density. So P by V is high power density, and compact. So then fifth point is all kinds of heat resources such as coal, oil, gas, solar, nuclear can be used with the MHD generators. So all resources can be used with MHD generators. So it is also a good sign. Then the sixth is that it has ability to reach the full power level instantly. So the to reach full power instantly. So it is also an advantage. Then seven, the operational and maintenance costs are low. So the operation and maintenance costs are low. Then eighth, but thus the cost of power generation per unit is also less. So as the operation cost is low, so the power generation cost will also be less. Then high capacity MHD generators are possible as there is no limitation to the size of the duct. So no limitation in size of the duct. So the much more capacity you want, you can build. So the capital cost of MHD plants are estimated to be competitive with those of coal fired and steam power plants. So the cost, this capital cost, is competitive, means it is more or less the same of the coal power plant. So it is also an advantage. So now what are the disadvantage? So we'll see disadvantages. So the first disadvantage is that MHD equipments have a shorter life due to high temperature stresses. So the life is shorter. So this is a big disadvantage. Second, it has high fluid friction losses and heat transfer losses. So losses are high of friction and heat loss. That is friction, and second is heat loss. So the losses are high. It has very high operating temperature. So the operating temperature is very high to maintain. So that is also a disadvantage which restricts the choice of material for various equipments. So the choice is restricted and high cost equipments are to be bought. So there are technical limitations on enhancing the fluid conductivity. So the fluid conductivity you cannot enhance, and the strength of the magnetic field. So that is sigma and B, you cannot increase. So there is a limitations in increasing both. So these are the few disadvantages. Now we'll see few design problems and developments which are being faced in MHD, that why it is not generally widely used everywhere. So MHD design problems. So what are the MHD design problems? So for economical and practical use of MHD generation, we will consider few problems. So MHD generator channel. So MHD generator channel combustor electrodes and air preheater are exposed to corrosive combustion gases. So all channel combustor electrodes and air preheater, all are exposed to corrosive corrosive combustion gases. So what will happen, and this also at very high temperature. So what will happen to this? So the materials must be developed to permit an adequate operating life for the components. So few components need to be developed. So components need to be developed which will have a high operating life due to this environment. So the ash or slag residue from burning coal is carried over with the combustion gases and tends to cause erosion of the exposed surface. So, however, the deposition of the slag, so the deposition of the slag on such surface may provide some protection. So, it may provide some protection due to the slag. Uh, Another problem is separation of the seed material. So, that is potassium sulfate, K2SO4. uh, so potassium sulfate from fly ash and its reconversion into the original carbonate, so into reconversion of the original carbonate form, and the difficulties associated with the slag and seed recovery can be eliminated by using fuel gas derived from coal rather than coal itself. So we should use fuel gas from the coal rather than using the coal, so in the combustor open cycle system. So a more advanced concept is to use hydrogen gas, so to use H2 gas uh, made from coal and water. So if we use H2 gas from coal and water, coal plus water, when this is burned into oxygen, the product would be a high temperature steam. So after seeding and passage as working fluid through the MHD generator, the steam would be used to drive a turbine generator, thus avoiding the need of waste heat boiler. So the waste heat boiler will not be required because as after seeding and passage are as working fluid, so the MHD generator, the steam would be used to drive the turbine generator only. So the boiler will not be required. So the power output, the power output of an MHD generator is theoretically proportional. So power output of the MHD generator is theoretically proportional to the square of the magnetic field. So P is proportional to B square. Hence the strong magnetic field is desired. So superconducting magnets which use very little current will be necessary. So this is the main design problem and in the development of MHD. So materials are required very much high. So we will discuss materials and prospects of the MHD generation in the next lecture. So thank you very much.